Hello fellas, Circle here, and today's episode will contain a lot of circular content. Why a lot of circles? Because this Pseudo-Focus series will shift from parameters to polar functions. Let's refresh your mind. What are polar functions? Well, polar functions are functions that are polar. Wait, no, that doesn't say much. So a polar function is a relationship whose input is some angle theta and whose output is some distance r. In visual terms, instead of a horizontal line attaching a drawing vertical line from its end, we get a rotating line changing its radius, drawing the polar curve from the line's end. An example of a polar function is r of theta equals theta. To draw this function, we must think of a constantly rotating line whose magnitude is constantly growing. This here generates the Archimedean spiral. Another example is r of theta equals 1 plus sine theta. Here, the rotating line alternates from radii of 0 to 2 units in a way that it draws a cardioid consistently in every rotation. But just in case your memory of polar coordinates is still rusty, no worries, because throughout this video, I will be laying out other examples of polar functions along the explanations, so hang in there. This shift of topics seems abrupt. Why suddenly transition from polar to parameter? Well, that's because parameters are actually related to polar functions. A fundamental definition of its coordinate system is that any radius with an angle can be split to its x and y components, which are r theta cosine theta and r theta sine theta. Because these are expressions of x and y, they can be conjoined with the parameter of r theta cosine theta, comma r theta sine theta. So in a way, we are still standing in parameter territory. Kinda. But this parameter here will be the foundation of everything that is derived in this episode. And this everything will compose of evaluating the quote-unquote derivatives of the polar parameter, then coming up with the parameter of its evolute, and then deriving the pseudo-focus solving equation from that parameter. And doing this everything process, we will revisit the visual details that formulate the ideas behind the pseudo-focus. With all that is said, let us now discover the general polar curve pseudo-focus. So our first objective is to differentiate this parameter. But for a start, I want to make a couple changes to it first. Briefly speaking, I will simply shorten r theta to r, and sine theta and cosine theta to s and c. Since both of these have theta in them, both are involved in differentiation. Okay, with both these changes, let us now separate the parameter to x equals rc and y equals rs for us to take the derivative of. Since both contain the variable to be differentiated, we use chain rule to each of these. So for x equals rc, the first derivative will turn out to be r prime c minus rs, where r prime is the derivative of r. Next, we differentiate that thing again, where it becomes r double prime c minus r prime s minus r prime s minus rc, where r double prime is r's second derivative. Oh, and we also combine the r's like terms, so negative 2 r prime s. And then we stop there for the x component. After that, we differentiate the y component, y equals rs. Then, using chain rule, the first derivative will be r prime s plus rc. Then, we differentiate again to get the expression of r prime s plus r prime c plus r prime c minus rs. And similar to before, the r prime c is combined to 2 r prime c. Now the reason I stopped at the second derivative is because what we derived is enough to plug things in the evolute parameter, and doing so is the next step we'll take to get to the pseudo-focus. Okay, this is the part where the algebra segment is supposed to happen. But you know what? Since I wanted to revisit visual details in this video, I have a slight reconsideration. Instead of focusing on the steps and processes of converting the evolute, I will reduce the algebra to a speeded up recorded segment. This segment is the part where I switch to subscript notation when writing primes, because a program I used, Desmos, cannot recognize prime notation. Overall, I'm saving your time and your soul by doing a quick run of evaluating the evolute parameter. So all in all, let the algebra begin. Ultimately, we will end up with the evolute parameter of RC plus R squared plus R prime squared all over R squared plus 2R prime squared minus R double prime times the coordinate negative R prime S minus RC, comma R prime C minus RS. Once again, I want to provide context of what this parameter means, and I'm gonna do that by breaking up the very gadget we've constructed. So first, this RC, RS coordinate here represents the polar curve that the evolute corresponds to, which is basically it. After that, this first coordinate is then added with this second coordinate with a huge factor on it. And like before, this coordinate here can be thought of as a normal vector whose direction is always perpendicular to the polar curve. This normal vector is scaled by this huge factor, which represents the curvature of the polar curve, which is better understood by drawing the almighty oscillating circle. For instance, when the oscillating circle is small, the point it kisses is very curved, and if the circle is big, the point it kisses is very flat. The radius drawn along this polar curve is the exact mathematical representation of the second evolute term, as the line is always perpendicular to the curve and always connects the original RC, RS to the evolute parameter, So the key idea is, when the oscillating circle is the smallest or biggest, the circle centers at the evolute's peak, where the pseudo-foci lies. So at the moment the second vector reaches its biggest or smallest magnitude, the parameter pinpoints the pseudo-focus's location. But one problem is, this scaling factor does not tell the whole story of its magnitude. This is because the vector alone also contributes to that magnitude. If you remember, the magnitude of any vector is the Pythagorean theorem of the two components. So in our case, the normal vector's magnitude looks like this. And like in the recording, the expression reduces to the square root of r prime squared plus r squared for the vector magnitude. This magnitude, then, is the term we use to multiply with the big factor to evaluate the total magnitude. Surprisingly, the big factor's numerator and the square root both have r prime squared plus r squared in them. So basically, the numerator compresses to r prime squared plus r squared to the power of 3/2. And this is the magnitude of the second vector term. Now a reminder that this thing represents the distance from the curve to the evolute. And to restate from before, whenever this expression is the smallest or biggest value, the evolute reaches its peak. So mathematically, when the magnitude's derivative is 0, the evolute parameter yields a coordinate that pinpoints its pseudo-foci. And since this requires some massive algebra to achieve, I guess I have to record another algebra process. Because we're taking an expression's derivative and equating it to 0, we will end up with an equation that you may know will be similar to step 2 of the 3SR. With that sort of context, let the second algebra segment begin. And so, the equation reduces to 3r prime times r plus r prime prime times r double prime minus r prime squared equals r times r prime plus r triple prime times r squared plus r prime squared, with the condition of r squared minus r double prime plus 2r prime squared not equal to 0. Okay, this is new. So what is this condition thing for? Well, this is something that I should have noticed since the very beginning of this series. The purpose of this condition is to determine whether a pseudo-focus exists or not. But I will explain more about this condition throughout the series, but more importantly, I should ask, what does this equation mean again? Well, it's an equation whose solutions yield values for the evolute. Values where the evolute is at its peak, where the pseudo-foci lie. But other than that, look at this, and compare it to the parametric form. Obviously, the polar form is more bearable and not tedious, and to my case, makes me feel more comfortable producing videos related to polar functions overall. And in those videos, I will be relying on the new 3-step rule that is compatible with those functions. Finally, it's now time for me to present to you the polar 3SR. Given a polar function r of theta, number 1, find r prime theta, r double prime theta, and r triple prime theta. Number 2, solve for the equation 3r prime theta times r theta plus r double prime theta times r theta, r double prime theta minus r prime theta squared equals r of theta times r prime theta plus r triple prime theta times r theta squared plus r prime theta squared. 2.1. Solution is extraneous if r theta squared minus r theta times r double prime theta plus 2r prime theta squared equal 0. Step 3. Plug the solutions s to the parameter rs cosine s, rs sine of s plus r of s squared plus r prime s squared all over r of s squared plus 2r prime s squared minus r of s r double prime s times the coordinate negative r prime s sine of s minus r of s cosine s r prime s cosine s minus r of s sine s. And there you have it. The sort of 3SR for any existing polar function out there. Which means we can finally wrap up this lengthy video after this short example. Let's take the polar function r of theta equals 69, which is a circle of radius 69. I mean, hey, this is a circular video after all, so you should partly expect this. But anyways, since we have a constant for a function, its corresponding derivatives should be 0. Because of this, the entire step 2 equation leads us to 0 equals 0, while the condition leads us to 69 squared equals 0.
None.
These two things basically mean, hey look, we don't have a solution, but we can confirm that the 0 solutions we have are by the least real solutions. Anyways, what about the evolute? Well, when you just plug in the general terms, it gives us 69 cosine theta, 69 sine theta, plus 1 over 1 times the coordinate negative 69 cosine theta, comma negative 69 sine theta. Well, look what we have here. The evolute turns out to be the single point 0, 0. This makes sense because every line perpendicular to the circle converges and intersects to its center. In other words, since the normal map of the circle outlines its center, this center point is actually its evolute. So wait, then would the center be considered a circle pseudo-focus? Well, rationally speaking, I'm not very certain. Step 2 says there are no solutions, but a solution exists. While Step 3 says that since evolute is a point, the PF is also that point. Perhaps I'll leave it as an open argument. And that finally wraps up for this video. A lot of ideas have been unpacked, and the new frontier of curiosity has been traversed. Expect some way lighter videos in the future because the 3SR is also lighter. Oh, and also expect more circles too because... circles. Other than that, this is probably my longest video and I don't think I'll exist for a while. Probably for 8 hours from 11 PM to 7 AM, and then I'll re-exist again. And then I'll produce more weekly videos like always. Such is a hyperglycemic cycle of the sugar lump. And that's that. I hope to see you on the next video. See ya!